back to the remainder of the morning session. The next talk is by Moortgat from Utrecht, who's going to talk about generalizing Lambek-Grishin.
Yeah, thanks. And thanks for the organizers also for inviting me here. I come here basically to learn, so I hope to be a wiser or a less stupid person on Sunday when I go back then than when I came here yesterday. But to do that, I thought that I'm going to give a tutorial style introduction to the kind of work that we are concentrating on now in Utrecht, so as to make it easier for you coming from a different community to see what the motivation is and to where the connection points are. The talk will be about generalizing Lambek-Grishin. Now, Jim Lambek is a mathematician, so he's certainly the right kind of person to establish the bridge between communities here. He devised this syntactic calculus, and recently the pregroup version of it. These are systems which are mathematically extremely elegant and beautiful, etc., etc. So why don't we stick with them? Why don't we want something else? Well, in a certain sense, the problem was already mentioned in Stephen Clark's talk this morning. All these original systems, they are in their expressivity, they are strictly context-free. And it so happens that natural languages have quite a number of phenomena, both in syntax and in semantics, which go beyond that boundary of context-freeness. Just to introduce the problem for people who are not linguists, here is a kind of problem that you run into. We speak about discontinuous dependencies, or dependencies between items which are not taking place in immediate contact. One of the kind of problems that you have is extraction context. Compare these two sentences here: who stole the tarts versus what did Alice find there. Intuitively, it's clear that these question words in a certain sense, they ask you to reason about a certain hypothesis which they ask a question about. So in pseudological form, you could say something like, who is the, give me an X such that X stole the tarts, or give me an X such that Alice found X there. The difference between the two sentences is that the first one, this hypothesis which you reason about, is nicely at the edge of the sentence, X stole the tarts. Whereas in the second question, it's somewhere in the middle of that sentence, where the dash is. And it so happens that the original Lambek systems just have no way of reaching that position. They cannot reason about it. A kind of complementary problem is in fixation, and this has to do with this pervasive ambiguity that Stephen was mentioning. So if you have a sense like Alice thinks someone is cheating, there is two possible interpretations here at least. One would be that Alice has this certain thought about, well, some person or other who is cheating. That's the local reading where the someone is just doing its semantic work within the clause where it's occurring actually. The other one is the non-local reading where there would be some particular person X such that Alice thinks that person is cheating. A non-local reading, which again establishes the kind of dependency of the discontinuous sort which the context-free systems are not able to deal with in an elegant way. Now, there have, of course, been lots of strategies for tackling that kind of problem. Restricting myself to what has been known in Utrecht is, say, between 1995 and 2005, we were exploring a strategy which, in a sense, is similar to the strategy that you have in linear logic, where you introduce modalities. So you have a bang and a question mark modality to give you back the expressivity of contraction and weakening, but in a controlled form. It's not going to be there anymore for free, but you can have it if you want to. So similarly, what we did for the Lambek systems is we added modalities, a diamond and a residual box operation, which gives you back the associativity and commutativity, which are lost when you go to the absolutely minimal context-free system, but in a controlled form. So rather than have these options in a global sense, you have them now in a controlled sense, comparable to the bang and the question mark modalities in logic. That's one way of doing it. What we are doing now is actually something a bit different. What I'm going to talk about is a symmetric extension of Lambek's original systems, in which we consider not just residuated operators and the duals, also Galois-connected operators and their duals, and in which we are going to replace the structural rules, these structural rules controlled by modal operators, by logical principles of distributivity. So in a sense that's a game, because structural rules you can postulate as many of them as you want. If you want to deal with the space that you have to, well, to handle problems of discontinuity is just much more limited than what you have in the structural rule approach. So that's one item I want to focus on. The other has to do with semantic interpretation. We are going for these symmetric systems in which you have a multiplication and also a co-multiplication. We are going to see that they naturally are interpreted in the continuation semantics, and that makes the burden on your syntactic calculus just much less than what you have in the original Lambek set. You can push a lot of work to actually to the interface to semantics, and the syntax itself can be kept extremely simple. Here is a slide with just some of the results that we have so far. I show it because some of them are being discussed in the next talk by Arno, and on the bottom of the page you see where you can find the references. For the symmetric calculi we have different proof theoretic formats. I will speak about the display calculus here, and I will speak about the proof nets, which are in correspondence with that display calculus. There is also the tableau method, which Arno has in the paper. There is focus proof search, which will be the topic of the next talk. Then on the model theoretic side, there has been work on completeness with respect to standard Grecian style relational models. We hope to hear tomorrow Mike speak a bit about generalized Grecian semantics for such systems. There has been a lot of work on algebraic semantics too by Wiskovsky and students. Phase semantics, I know in the talk that he will present here. The talk here is the Unix here. There has been work on expressivity and complexity, and I just mentioned that this was done in some recent master theses here. The issue is that if you do not consider the distributivity principles for these symmetric systems, you stay with context-freeness, and you have polynomial recognition problems, so that's very nice from a practical, say, efficiency point of view. If you add the distributivity laws, then you go beyond what is known as the mild context-sensitive grammar formalism. Exactly where you end up is unknown. The upper limit here is unknown. And in terms of computational complexity, you have an result. So that's the background. Now, I just wanted to have a very, very brief recap, which is actually more meant for the linguists than for the mathematicians that we find in the room here, about the crucial concepts that will play a key role here in the talk. And these come from, say, from situation theory. And what we will be looking at in general is operations for forming type-forming operators that either form pairs of residuated operations, Galois-connected operations, or duals of these two notions, according to which of the biconditional relations that holds. Lambek calculus uses only the residuated operations, and in that sense you could say the generalization that we are going to consider here just looks into that algebraic universe there and takes the other natural inhabitants of it, which by accident one could say were not present in the original Lambek systems. Another way of looking at these operations is to say that the residuated pairs are isotone, are order preserving, the same for the dual residuated pairs. The other operations, the Galois-connected ones, are order reversing, and their compositions have certain properties that we find on the slide. Don't mind about the details here, it comes back on the next slide. So, what is this mysterious Lambek-Grishin calculus? Lambek calculus on the first line here. The basis of it in the simplest system at all, has a product operation for combining phrases. And this product operation has a left and a right residual, the two slashes that we saw already in the previous talk this morning, except that we are using the mathematical notation. These are fractions, so they have a numerator and they have a denominator. Because the system that we have is not a commutative system, the numerator can be right divided by the denominator, or it can be left divided by the denominator. So we always put the denominator under the fraction sign, another notation than the one that was used by Steve. And what did Grishin do in this old 83 paper? He said, look, this is a nice system, but why don't we just complement the type of forming operations with a dual set? So that would be a co-product, which I write as the circle plus here. And the co-product, just as the product is forming a residuated triple, but now with respect to difference operations. So this would be the C minus A. The A is the quantity which is subtracted, or the quantity which is subtracted, the B could be subtracted from the left. I don't know how to pronounce that, B from C or whatever, but see what the title is. So you could say from a logical point of view, what we have here is a multiplicative conjunction, the tensor, but now in this case we also have a multiplicative disjunction. And this comes out, in fact, when you look at the style relational semantics, where you find exactly these two ideas. Now, let's play the game of through the looking glass here for a moment. You could say that the original Lambek calculus already had one kind of symmetry, and I'm using here the words that Grecian uses in his paper. And the symmetry is the symmetry between left and right. So it's the symmetry which relates a fraction which looks for its argument to the right to the fraction which looks for the argument to the left. That's a left-right symmetry. This symmetry is order preserving. So if we see the arrow here as a derivability relation, then for types A, B, for which there is some proof that A produces B under these residuation inferences, there is also going to be a dual in the sense of the left-right symmetry derivation that relates the both are symmetric forms. Grecian, when he added the multiplicative disjunction to that system, introduced a second symmetry, which is an arrow reversal. So for every proof, for every derivation that sends you from A to B, there is now going to be a dual one, which sends you from B, how shall we say that in English, B goggles to A goggles under the arrow reversal. And just to avoid a lot of boring definitions here, Grecian uses a translation table which makes the intuition here as to what is dual to what, which makes it clear. Now that saves us a lot of work, these two symmetries, because in fact looking at these systems, and my slides are simple in that respect, all the theorems but also the proofs and the terms that go with the proofs, etc., they come in quartets. You can just pick out one of them and all the others are generated by just applying the symmetric forms. So on the slide here, what you see is one of the laws which Stephen was discussing, this law of type lifting, which comes in two left-right symmetric forms on the bottom line here. But now with Grishin's generalization, there is also the dual of that, which is type lowering, which again comes in the left and right symmetric. Yes?
Just a quick verification, the slashes have different meaning in here than in CCP,
yes,
right?
that's what I was saying. Right? So we use mathematical notation, it's fractions. They have a numerator, a denominator, and what is under the slash is the denominator.
Okay, right.
It requires some mental adjustment, but I suspect that in the audience here, not many people are familiar with either of the notations. So. Okay, so now comes the crucial part where I hope I will be illuminated by Sunday listening to all your interesting talks that follow. Just introducing the symmetry, as we saw, still keeps you with a context-free system in terms of expressivity. So Grecian did something more. In fact, what he considers is forms of interaction between his multiplicative conjunction and multiplicative disjunction. And he has, and this is interesting here, he has two ways of implementing that idea of communication. Each of these ways will have to respect the resources, so we are dealing with a linear system, so that means the distributivities will be linear, they will not copy or duplicate any material. Linear distributivity is the work which Coppet and Seeley and Paiva, etc. use for these principles. Also in our case where we have non-commutativity in the basic system, and even a non-associativity, we speak about phrases and not about simple strings, we want these interaction principles also to respect these problems. So how do they look like? Here they are. Let's first look at option A. And I'm going to try in a procedural fashion to introduce the idea here. You see, these are four ways of going from one premise to a conclusion. And what are they doing? Well, they say, well, suppose that we have an A product B, which is less than a C co-product B. So we have fusion on the left-hand side of the inequality and fission, co-fusion or whatever on the other side. Now, what we are doing in these distributivity laws is, I try to formulate them in the most compact way possible. What we are doing is we are simultaneously introducing the two residual operators in the conclusion. Simultaneously. So if this was just residuation, you could introduce the slash for the product. If it was just co-residuation, you could introduce the difference operation for the co-product. But what we do here, we do it the two of them together, which means that the two structures, multiplicative conjunction and disjunction, will become entangled in the surface. Okay. Now we already said we have the symmetry, so if you see why are there 4 ways of doing that, and in the picture, the proofnet picture, it will be even more nice. There are 4 ways because for the product or for the co-product or for the two of them, we can apply the left-right system. And that gives exactly these 4 possibilities of entangling the multiplicative conjunction and the multiplicative disjunction. So that's 4 possibilities, and there must be 4 of them, otherwise you have spoiled one of the symmetries here. But there's also 2 options, option A and option B. What's the difference between option A and option B? The difference between option A and B has to do with the flow of information. In the option A form, we start from the product and the co-product, so from the fusion-fission structure, and we introduce the residual. In option B, we just take the converses. We would start from the conclusions here as our premise, and we derive the conclusion. And that's theoretical possibilities that you have for communication here. There's nothing else that you could invent, which would also be respecting resources and respecting structure. The point is that in terms of conservativity, we can either choose for option A or for option B, but not for the two of them together. It's not so difficult to see if you would have them as invertible inference rules that there will be overgeneration. You will lose, in fact, the structure. Now, most of the applications so far have concentrated on option A, but there is also some suggestions that option B would be useful in linguistic applications too. And this is one of the open issues now. How could we combine them in such a way that we are not messing up the structure preservation? That's an open question. So distributivity, that was for the binary vocabulary. Then I said the generalization that is obvious here is that you can also generalize the arity of the operations. In fact, you could say that the unary operators come already before the binary operators, although they were not in Lambek's original work. In the talk that I will have later in the talk, we will focus not so much on the residuated pairs here, the order preserving ones, but on the order reversing ones, the negations, if you wish, in this setting, which means we have a pre-negation and a post-negation which are Galois connected, and also dually we have a pre-negation and a post-negation written one, which are dual Galois connected. Here is the Galois laws, they are order reversing, and here is the properties which these 2 negations have in terms of the compositions. So we see that with the Galois pair, we can easily obtain a closure operation, as is well known. And with the dual co-Galois operations, we have an interior operation, and they will prove to be very useful for.
Michael.
Yes.
So just to say that I'm with you, this is so non-commutative version of start from this category.
Yeah. So maybe in the discussion we can see more here, but if it's exactly that would be nice, because then we already know more or less where we are. But there is no associativity, so that would be the difference. No associativity. Why? This was in Stephen's talk this morning already. We want to have phrases, right? Not just strings. We want to have some more structure which says the strings are grouped in these and these phrases. So it's maybe it's a non-commutative, non-associative star or non. Okay, so if for the distributivity laws that we just discussed, if you also want to include the negations here, you can. We don't want to have units. That's another linguistic peculiarity. There is nothing wrong from a logical point of view, but it's known that if you have multiplicative units in your grammar, so that would be assigning a type to the null string, then overgeneration is everywhere, so you prefer not to have them. So that's why the negations which we use, we introduce them as primitive operations in their own right, unary Galois connected or dual Galois connected operations. We don't derive them from the multiplicative units. Still, if we want to see what the generalization is of the distributivity principles, we can just do that by seeing how they would be derivable in a system which has these units. So just to engraft that on your mind, this would be a crucial slide later for understanding what the connections are with the quantum world. What is the status of these distributivity principles, and more specifically, what would, from a mathematical point of view, what would be natural structures that either support option A or support the converse of option A, namely option B. Right. Okay. Now, let's let's look at some proof theory here, because that's why we are here. First the sequence calculus, and then proof nets, because I understand that most people here are extremely fond of nice pictures, nice diagrams. So you get the diagrams, but first the bureaucracy of the sequence calculus. And display sequence calculus. The first illusion that you may have is that, well, if Grecian symmetrized the Lambek calculus, the ordinary Lambek calculus, why don't we just take Lambek's sequence calculus and why we dualize it in the obvious way, and we would have our Lambek-Grishin calculus? It doesn't work. And it doesn't work because of these distributivity laws, and this is why. Take the rule which introduces an implication to the right. So if we want to, from gamma, to derive b under a, our premise will say, well, take the b as a left sister of the gamma, and prove a from that. Right? Now we are in a symmetric system. So in the symmetric system, it's not intuitionistically necessary anymore that this b under a formula is the only formula on the right. The b under a could be in some context. What kind of context? On the right of the turnstile, the context will be a multiplicative disjunctive context. Right? But our distributivity laws, they say if a slash occurs within a bigger disjunctive multiplicative context, then it can escape from that context. So still our b would be able to escape to the left-hand side by just applying here, implicitly if you wish, the Grecian distributivity laws. That's nice, that's fine. And this could give you the impression that you could actually absorb these distributivity principles in the original sequence rules. It's not true. This illusion, look at a couple of sequences like the ones that you find displayed here. In this sequence, there is just no way of giving a cut-free derivation. Why? The only connective that you can work on is the difference operation here, or is the slash operation here. And if you do that, if you apply the rules indicated on the top of the slide, there's just not going to be a cut-free derivation. And they are derived. So that's the problem. There's a solution to that problem, in fact, an elegant one. Display calculus for these kind of logics. And the crucial property of the display sequence presentation will be that for every logical connective, we have a structural connective. So not just for the times and for the coproduct, but for every of the 6 logical operations. That means that our residuation principles, Galois principles and their duals become structural rules, in fact equivalences from the display perspective, and also that the distributivity principles get the status of structural rules rather than logical rules. And that will make cut elimination go through, etc., etc. Let's see how. So as I said, in the display calculus we have structural operations for every logical operation. Mostly one uses overloading here, or one tries to be very compact in the notation. I try to be as explicit as possible in the notation. So what I do is I just use exactly the same symbols for the structural operations, but I set them apart with these marks here. A trick which I learned from the Romans when they do inscriptions. They put a little dot between the parts that have to be separated. So these are structural operations of product or co-product, etc., etc. And ultimately they are formed from formulas. So we build a tree or a dual tree with formulas at the leaves. And later when we discuss semantics, we will see that the formulas for input structures are labeled with variables and for output structures with covariables. But for the time being, we can forget about labels. So then here is the rule for the sequence calculus. There is an axiom and there is a cut rule, of course, which will have to be eliminated. As I said, the residuation principles and the Galois principles, here they are in their algebraic form with arrows between formulas. Here they are in their sequence form, which is exactly the same. We have just replaced the logical operations by the structural counterparts. Okay? And as you see the distributivity laws, I give one example here. The distributivity laws have all the logical operations in the position where in fact they are structural. And that means that we have structural rules here, and that cut elimination will have no problem in dealing with these nasty distributivity. What are the logical rules? Well, sequence calculus, so for every connective there is a left and a right rule, introduction rule, and they naturally fall into groups. I'm going to give just one illustration and then I leave it as an exercise for you to complete the picture here. One of the groups is just rewrites rules which are reversible from a logical point. The only thing which they do is they replace a logical connective by the structural counterpart. Is that a good thing to do? Yes, because we know that sequence proof search works backward chaining, works top-down. So if this logical connective in the search for a proof, if it can be replaced by a structural connective, we have subformulas A and B now which we can start working on, and we have simplified the task that we had to accomplish. The other rules, the real logical rules, are the multiplicity rules. What they say is if I find in the conclusion a matching logical connective and its structural counterpart, then I can break up my my problem into smaller sub-problems for the subformula. Okay? And that's the pattern for all these rules. Exercise, and if you get bored in the rest of the talk, complete the picture here. Cut elimination, I'm not going to do that, but it's rather straightforward to see how cut will be eliminated in such a case. So that's our sequence calculus. Now here is our problem sequence that did not have a cut-free proof in the naive presentation. Let's see how display presentation works. We can apply, the first step is in fact the crucial step. The first step here is going to say, not we work on the slash here, on the slash operation, which would be the wrong choice, but we can apply a dual residuation inference on the structural code product. So we bring our A in a different structure to the antecedent part. The next step, we can now focus on our backslash, and we can replace it by a structural connective. At this point, all the formulas which we want to reason on are accessible. They are all structural parts of the sequence that we have. So from here on, it's just applying the obvious residuation inferences. And now we have the situation where we have a slash, we have the matching structural operation, and we can break our proof into smaller parts, and then everything basically is done. Right? So that's the typical sequence presentation. As you see, there's many steps because this is absolutely the most explicit way of accounting for every structural or logical operation that you are taking in the derivation. But that's how it works. Proof nets. Suppose we want to do away with the bureaucracy of all these symbol manipulations. Is there a nice graphical way of expressing the same idea of a proof? There is, in fact, this is the reference is on the bottom of the slide. And I'm going to just give you like a 3-minute idea of it. And how it generalizes the notion of proof net that may be familiar from the other one. So the basic building blocks, of course, are links. They come in two varieties, tensor or cotensor links. There is premises, there is conclusions, and maybe there is a main formula, which is not necessary, but if it's there, it will be one of the premises or one of the conclusions. Now, from these links, we are going to build proof structures. These are sets of links over some finite set of formulas, and we want, of course, that every formula is at most once the premise and at most once the conclusion of a link. And then hypotheses or conclusions or axes are just the special cases of these proof structures that are indicated here. From a proof structure, which still is labeled with these formulas, we obtain an abstract proof structure by just erasing all the formulas at the internal nodes. Then we have a notion of rewriting on these graphs, which will be like the pooling of the strings in the other diagrams that we will see tomorrow, I think. The next slides give the examples. And the proof net then will be an abstract proof structure, which just under that rewriting or pooling of strings, if you wish, converts to a tensor tree. A tensor tree which may be unrooted, because we have a multiple conclusion system, so it's not guaranteed that there will be one root for that. Here's references, and I'm sorry, this is extremely difficult. The first author here is in English would be, Moot, not Moot, as I have heard this pronounced. The second author, oh my god, well, there's no way of writing that down, is Buiten. Buiten, right, and not, well, any mispronouncement. They have done proof nets for multimodal Lambek calculus quite some years ago, and in a recent paper on the archive, Richard shows how to connect these proof nets with the display calculus. So here's our links, pictures. There is an error in the pictures I saw this morning when I went through the slides again. So here are the logical links in either the tensor or the cotensor variety. If there is a little arrow here, that's the main formula of one of these links. Here on the bottom you see the contractions that go with it. So what are these contractions? Suppose that we take a cotensor and a tensor link for the product and that we click them together here on the A's. And we have this situation. And in this situation, which has main formula hypothesis here, we are able to contract to just one point. One point which is then labeled with the hypothesis and the conclusion in question. So for all these cases of contraction, this is what we will have after the contraction. Okay? So then, I already see signs of understanding here. This picture here for contraction goes with this combination of links. I just mixed them up. You have to do some mirror symmetry here. So what happens here is we click together the two B's, and then the A and the A is the same here. We can contract such a situation to the point which just has hypothesis conclusion. Okay, and similarly for the other co-implication. Duality. Next slide is just exactly the same for the multiplicative disjunction, and as you see, this is just switching up and down. Right? This is just turning everything upside down. Exactly the same. Structural operations like the Grecian distributivity. This is where I saw pictures that I saw in the abstracts of, or in the papers that go in the rest of the conference. So our Grecian distributivity now will take the following form, or I give one or two examples here. Suppose we have fusion of this structure here, and fission at the other side. Okay? Now if we have fusion and fission, there's two ways of rearranging that. We can take exactly the same pieces, which have hypotheses VW in that order and conclusions XY in that order, but now they are internally connected in this way. Or you can do exactly the same, but then in the other way. You can say, well, we can also put them this way. So from that structure we obtain that structure, which again has, let me see, V and W as hypotheses, X and Y as conclusions. So this is like internal rewriting, or internal restructuring of the net, mirroring the Grecian distributivity, or at least the two of them. Let's look at an example how the derivation with this proof net approach, how it works, and how it relates probably also to the nets that we will see for the pregroup presentations later in the conference here. We start from, of course, like in the first talk this morning, we start from lexical graphs. So here are the graphs for some words. John believes, someone left. And what we see here is we just have unfolded the formulas into the little partial proof nets that correspond to them. Some of them are very simple. Like here the verb believe, it's going to produce a sentence, but it still needs a subject, and it needs a sentence which will be the complement of believe. That's all clear. Here is the more interesting one because it uses our new vocabulary. So this word someone here, it says, well, I'm going to provide you with a noun phrase, but in order to do that, there's a difference operation here. I also want this to be connected, so there is this S and there is this S, and we have to connect all these parts together. How could you do it? Well, there's many ways of doing it. You could say, well, I plug John together with this MP, and then you have John believes. Or you could put John here, and then you have John left, etc., etc. But the sentence I'm interested in informing would be the sentence, what shall we say? John believes someone left. How can we do it? Well, here is how we have done it. Here is our John believes someone left, which produces ultimately a sentence. But there is this black link here which has to disappear, has to be contracted. How can it be contracted? It's discontinuously linked to the node that we see here. So what can we do? Well, first thing we see here there is this fusion-fission configuration which actually can be rewritten. And it can be rewritten a second time, and it can be rewritten a third time. Sorry for the low tech here. A third time. And finally, we obtain the situation where we have the contractible situation of our cotensor and our tensor link in local correspondence with each other, where they disappear, and we have our sentence that we wanted to generate. So this is clicking, if you wish. The process of clicking these lexical graphs together, and then rewriting or reshuffling or whatever the wires in such a way that the sentence, the final sentence. This is a proof net approach. And then finally, I will use, I think, 2 minutes to just say the basics here. But finally, the syntax-semantics mapping of this kind of system. The standard view that we heard this morning in the first two talks says, well, we want to have compositional mapping which takes some syntactic image calculus, a source calculus, and then through a homomorphism sends it to a semantic calculus for interpretation. The homomorphism for standard Lambek calculus is extremely simple. what you do is you, for the atoms, you just stipulate some correspondence with semantic basic types or complex types, whatever. And then what you are going to do is you say, when we move to semantics, we forget about the difference between a slash that looks to the left and a slash that looks to the right. They are just both going to be interpreted as functions. What kind of functions? Linear functions, to be precise. That's all very nice and very simple, but we saw already on the first slide, because of the context-freeness restriction, it would mean that for this kind of syntactic input calculus, that a lot of desirable ways of putting together the meanings are just not obtainable. They are lost in the translation. So the alternative that we have been exploring is in the Lambek-Grishin setting, which is symmetric, is to apply the standard continuation semantics for these quasi-classical systems, in which the basic distinction will be one between values and continuations, which are themselves functions from values to semantic types. The context by moving to continuation semantics will be an explicit part of the interpretation process, and as I said, what results from that richer image between syntax and semantics, we can relieve the syntactic source calculus a little bit, and we can keep it as simple as we want. I'm not going to give you any details here. I'm just going to say what the big picture is, and also say where I think the combination with the distributional model of semantics comes in. The picture that we work out following Lambek-Grishin and other authors is the following. We start from our symmetric Lambek-Grishin calculus, which is a multiple conclusion system, right? It has the multiplicative disjunction, so it's not a classical system, but it's multiple conclusion. What we are going to do is, in the first step, is we are going to map it to multiplicative intuitionistic linear logic. So we are going to turn a multiple conclusion system into a simple one conclusion intuitionistic system, for which we have the standard Curry-Howard correspondence with proofs interpreted as programs. In that mapping, we introduced a new crucial ingredient here, which is this answer. Second step of the interpretation process is that we are going to say, well, now, once we have done that, we want to see how we can combine the derivational interpretation, the interpretation of the way the structure is produced, how we can combine it with lexical semantics. So here is, I think, the connection point with the distributional models. For the lexical semantics, what we are going to say is, well, the first map is linear. It remains all the resource sensitivity of the source calculus. The second map, for logical words, linearity is not an issue anymore. You could have non-linear logical recipes. But also at the second step, the lexical semantics, there will be lots and lots of non-logical constants there, for which a distributional meaning model would be extremely reasonable. Only it would be combined here with, say, a derivational interpretation, which is much more structured than one that we saw in classical systems. Details I cannot give here, which is sort of bad. I'm just going to the conclusion part. The conclusion part is with, well, just summarizing what we more or less said. If we want to tackle the expressive limitations of the original Lambek calculus, we want to do it in a way which keeps the mathematical structure of this whole method. So we don't want to start, say, playing dirty tricks or adding, say, non-logical mechanisms to a system which basically is a proof theoretic mechanism. And we've seen actually that the move to symmetry, which Grecian introduced, gives two ways of doing that, both on the form and on the meaning side of the coin. On the form side, we have these distributivity principles that relate to dual families of operators, which means that the options that we have to formulate forms of structural reasoning are extremely limited. There's all the preservation properties that we have to respect, and well, that limits our choices, and that's a good thing. On the meaning side, because now we have the continuation semantics for a source calculus that is multiple conclusion, we can have much simple syntax, because in the mapping to semantics, a lot of things can happen that do not have to burden the syntax. And this is where I will stop. I don't know where the question should be taken, but otherwise we take it just at the end.
Okay,
that's up to you.
Since the next talk is a continuation of this one, do people want to ask questions now?
I see that there is actually.
Oh, there is actually a question.
Yeah.
No, we've got time.
Yeah, so it's up to the other.
Bob.
Could you give some feel on graphically as compared to the proof that you have the non-associativity component?
It's okay. It comes in. Where does it come in? Yeah, I have actually an example for it. Take a sentence with a reflexive pronoun here, like Mary hates herself. Okay. So what you could say is, here's our transitive verb, Lambek type. Let's say transitive verb. You could say, well, this herself word here, it's a function, higher order function, that needs such a transitive verb, and that will give back an intransitive verb, which still needs the subject. So we would type it as transitive verb, giving back intransitive verb, where the letter is just empty. And then with our MP sentences, everything is fine, everything is good. Now, where does non-associativity come in? Suppose that we have John thinks. No, Mary thinks, sorry. Mary thinks John hates herself. No good. And because herself would be, well, it would be not just a noun phrase, but a noun phrase feminine for herself, masculine for himself. But if you have an associative system, the whole string here thinks John hates will be reducing to the type for a transitive verb. So there's absolutely nothing, if there's no structure, no phrase structure, absolutely nothing that will prevent you with the herself here to refer back to the subject, which is a long distance away, because the string here will reduce actually to the transitive verb under associativity assumption. So once we drop the associativity, you don't have that overgeneration anymore. Lambek saw it in 61 when actually he formulated the non-associative version exactly based on this kind of overgeneration. Of course, it's not that we never want to have such associative reasoning as Stephen was already. If we want it, we want to have it in a controlled form. And that's what these distributivity laws give you. They give you, like, not the full, the global associativity, but some controlled form.
Then maybe I have a question, because you said if you both add the one thing
Yeah,
and the
and
other, then
converse
you get some associativity, but only in the scope, only in you don't get full associativity, right? You only get it like in the image of one of the operators.
Yeah.
But maybe that's exactly what you want. Maybe you want some associativity.
But still you
Because
get
that's
too
what
much.
you're trying-
Still you get too much.
It's too much.
Yeah, you get too much. So it seems that if you have say no commutativity and associativity, and then if you have the distributivities in the converse form also, then this doesn't harm associativity. But if you drop everything, all structural assumptions, both associativity and commutativity, and then have the four distributivity laws, which are like syntactically mixed associativity plus mixed commutativity, then you spoil the picture. For reasons which are still not completely clear to us. But Arno has good examples, not too difficult to come with examples where it goes wrong.
Sorry, so the proof that you showed for John believes that someone.
Yeah,
So at the end you get something that looks like a tree. Is it the same tree that you get if you just parse it using
No.
categorical?
Yeah, sure. Yeah. It's the same tree, but the interpretation that you will get for the tree has the wide scope for the embedded somehow. So the way in which you have put together the tree under the Curry-Howard isomorphism gives you a reading where someone is such that John thinks this someone left, which is not obtainable in the Lambek-Grishin. Lambek-Grishin just gives you the local reading and associated with that string, but that's it, not the non-local reading.
Well, it's arguable that that's not a syntactic method.
No, it's not syntactic, right? It's a semantic method, that's obvious, right? And that's how it comes out here. It's just the Curry-Howard effect of putting together the net in that way, that for one and the same string will produce the two meanings.
Okay, thanks very much.